All right, into chapter 10. We are flying through AP statistics here. So you're going to see a lot of what we do in this chapter is very similar to stuff that we've done in previous chapters here. So in the last chapter and in chapter 8, we were running inference for a single sample. So we were finding a confidence interval for a single sample. We were running a significance test for a single proportion or a single mean. In this chapter, we're going through that same process, except we're doing it for two populations or two groups or two samples. So for example, instead of saying something like, do we have convincing evidence that the proportion of people who own a dog is greater than 30%, I'm going to compare, is the proportion of people who own a dog in New Jersey greater than the proportion of people who own a dog in New York? Or for a mean problem, maybe we want to create a confidence interval for the difference in the mean SAT score at South compared to the mean SAT score at North. So now we're taking two distinct samples and we're running inference for that. So let's go into the notes here and see what we got. First thing in section 10.1, there is a lot in here. We're going to be comparing two proportions. So the first thing we want to talk about is everything is based off of that sampling distribution of the difference between the two proportions. So that sampling distribution describes all the possible values of your one sample proportion minus your second one and how often they occur. So for example, if you think about going back to comparing the proportion of people in New Jersey who own a dog versus the proportion of people in New York, that sampling distribution, which is going to follow that normal curve as long as we meet those conditions, which we're just going to see, that sampling distribution will display all of the different possible values of your proportion in New Jersey minus your proportion in New York and how often they occur. So when we're talking about the shape, the center, and the spread of the sampling distribution, the mean of the sampling distribution of P1 hat minus P2 hat is just equal to the population proportion of your first one minus your population proportion for your second. So if we know that 40% in New Jersey own a dog and 38% in New York, the mean of our sampling distribution is going to be 0.40 minus 0.38 or 0.02. The standard deviation of the sampling distribution, this is a long formula, but don't worry, it is on the formula sheet. So if we go to sampling distributions, and everything we've been doing is for one population, now we're talking about two populations, here's that formula right here, okay? And here's that formula we just saw, the mean of the sampling distribution. Here is the standard deviation of the sampling distribution, which is on the formula sheet for you to use. The shape of the sampling distribution, we've seen this formula before. We're talking about proportions, NP greater than or equal to 10, N times 1 minus P greater than or equal to 10. But now I have to check it for both proportions. So I'd have to take my sample size for New Jersey times that 0.40, for example, and then times 1 minus 0.40, and then I'd have to do it for New York. That sample size for New York times 0.38, and same idea, sample size times 1 minus 0.38. All of those have to be greater than or equal to 10. We still have our 10% condition for our standard deviation formula, so we need our sample size to be less than 10% of the population. This picture in here just illustrates what we're dealing with in terms of the sampling distribution. The mean of the sampling distribution is where we're centered. That's that P1 minus P2. And then we've got the standard deviation formula for the difference of our proportions, which we see right here. We'll go through the example in class related to American-made cars. Continuing on here, along that same kind of concept here, is a confidence interval for the difference of proportions. So we've been checking conditions in all the different confidence intervals that we've gotten, and you should kind of have the idea. Now we want to say, okay, I want to create a confidence interval for the difference in the proportion of people in New Jersey who own a dog versus New York. So what do I do? What conditions do I have to check? Well, I have to make sure I either have a random sample for both of these or random assignment or a randomized experiment. If we were doing something like, for example, thinking about COVID, the proportion of people who developed COVID with the actual vaccine versus the proportion of people who developed COVID versus with a placebo vaccine. So that's the type of idea, confidence interval for the difference of proportions. Check your normality, N1 times, we're back to P1 hat, greater than or equal to 10, N1 times P1, 1 minus P1 hat, and then the same thing for your second one. So you have to check this 4 times here. Again, independence condition, if we're dealing with sampling in a random sample, not the experiment, we have to make sure our sample size is less than 10% of the population size. When we just talked about sampling distribution for proportions, we saw, okay, we had the standard deviation for the difference of proportions, this is the standard error. The only difference is we use p hat here, which is more common because it's very rare that you'd know the actual population value. Similarly, that formula is right in here, standard error for two populations, proportions. It's not a formula you need to memorize. It might be something you see on a multiple choice, but that's right in there. What does that measure? That measures how far the difference in your sample proportion typically falls from the true difference in the proportions between those two variables or those two samples. So what is our confidence interval formula? It's not on the formula sheet, okay, but if we want to create a confidence interval formula by hand for the difference of proportions, we're going to take our two sample proportions, subtract them, plus or minus the critical value times the standard error. So all we're doing here is the same thing we did with one sample, just a more complicated formula. And remember, your confidence interval formula is given here, statistic plus or minus critical value times standard error. So what is a statistic? To subtract your p-hats plus or minus the critical value times the standard error. And that's how you would go about doing it by hand. I don't recommend you do it by hand. I'm going to show you how you can do it on the calculator. And we'll see this example in class, but I want you to write down how to do it on the calculator. On the calculator, the only drawback to it is there's no opportunity for partial credit, but it is significantly easier to do it on the calculator, so that's my recommendation. On the calculator, if you're going to do this, you would go to Stat, over to Tests, and a 2prop z int. And what that stands for is 2, which is letter B right here. 2, because we've taken two samples. Proportion, z, is our test statistic or critical value, interval. If I go there, you'll see it's going to ask you for a couple of things. Your sample size for your first population, your sample size for your second population, and then your confidence level. So for example, maybe we found that 20, or maybe we'll do this, 44 out of 100 people in New Jersey own a dog, and 38 out of 125 people in New York own a dog. Your sample size don't have to be the same. And we want to create the 90% confidence interval. I would just plug in those values there, go ahead and hit calculate, and there's my interval. We are 90% confident that the interval from 0.02995 to 0.24205 captures the, what are we talking about? True difference in the proportion of people in New Jersey versus New York who own a dog. Okay, and we'll do plenty of examples in class to work through these types of problems. But use the calculator. Don't do it by hand for these. It's just too much work and too much chance for you to make a mistake. Along those same ideas, we can create a significance test for the difference of proportions as well. So what are the conditions? Well, here's a hint. They look exactly the same as the conditions that we just saw. So random sample or random assignment / a randomized experiment. Check my normality condition for proportions, n times p hat greater than or equal to 10, n times 1 minus p hat greater than or equal to 10, and then same thing for your second proportion. Independence condition, have to check it for both. Are both of my sample sizes less than 10% of the population size when we're dealing with random sampling? In a randomized experiment, you do not have to check that. So what are our hypotheses going to look like here when we're running a significance test for the difference of proportions? Well, our null hypothesis assumes that there's no difference, so that the proportion in New Jersey is equal to the proportion in New York. So we would run something like this as our null hypothesis. You can write it one of two different ways. I prefer it this way here. P sub 1, the proportion in New Jersey, is equal to P sub 2, the proportion in New York. Then what are we trying to prove? Am I trying to prove that the proportion in New Jersey is greater than New York, less than New York, just different from New York? Whatever you're trying to prove, you've got those same three options for your alternative hypothesis. In here, we have this idea of finding the standard error for what's called a pooled combined sample proportion. Not overly important, and this formula is on the formula sheet right here for the pooled proportion. And you see we use this one, not the one that we were just using, when we assume P1 and P2 are equal, which we do in a significance test. Hence, your standard error formula here is slightly different than the standard error formula that we saw for the confidence interval. Because for a significance test, you're assuming equality between the two proportions. So the standard error that we use here is for the pooled proportion here, the pooled combination, where we take our x1 value plus our x2 value over n1 plus n2. So for example, if I went back to this problem here, my pooled proportion, I would have to take that 44 and that 38 to get 78 over 225 to be the pooled proportion that I would use as P sub C hat, okay? So that's the only difference in there. The reason I'm showing you this is in the very, very unlikely chance that you would need to do this by hand, which is a really ugly formula that I don't recommend. Your test statistic to find that Z by hand says take my statistic, which is the difference of the sample proportions, minus the hypothesized value, which is 0, because we're assuming there's no difference, over the standard error. And again, we have to use this new standard error because we're assuming that P sub 1 is equal to P sub 2. What does this measure? This Z-score measures how many standard deviations our sample difference is from the null hypothesis, assuming the difference is equal to 0. There's a lot in here, but it's really not as challenging as it looks, okay? You'll see that it actually is pretty straightforward and pretty easy to answer these questions. So there's an example that follows that we'll do in class where we're actually running a hypothesis. But my recommendation is use the calculator. Use the calculator to run these tests. So for example, say I wanted to run the test, and I'm just giving you a quick idea of what we're talking about here. I want to say I think that the proportion of people in New Jersey who own a dog, so I'm going to say proportion of NJ, is equal to the proportion in New York. And I could use subscripts like that. And my alternative, what I'm trying to find evidence of, is the proportion in New Jersey is greater than the proportion in New York. So just to kind of give you an idea of how this would work, and we'll use those same values that I got or I made up here. Maybe my sample proportion for New Jersey, so my P hat of New Jersey was 44 over 100, and my P hat for New York was 38 over, what did I say, 125? So obviously in my sample proportions, New Jersey, the percentage in New Jersey was higher, the proportion in New Jersey with the dog was higher. But is that strong enough evidence? Okay, is it a large enough difference to then generalize that result to the entire population? So I'm just giving you a quick idea of how this works, okay? We'd write our hypotheses, we would define our parameter of interest, we would define our significance level, we'd check all our conditions, but I want to show you on the calculator where you would go from here. So on the calculator here, I would go now, I want to run the significance test, so I'm going to go to stat, over to tests, and I'm going to go down to a 2 prop Z test. So 44 over 100, you'll notice it's all in here because I did it for the confidence interval. Here's my first one, 44 over 100. Here's my New York, 38 over 125. I think New Jersey is greater than New York, so I'm going to put P1 greater than P2. Calculator draw, it doesn't matter, whatever you want. Here's my test statistic. Here's my p-value. Same exact idea that we were doing. You would copy down your test statistic, Z. You would copy down your p-value. You would go through and you would either, in this case, decide to reject the null hypothesis. Therefore, we have convincing evidence that the true proportion of people in New Jersey that own a dog is greater than the proportion in New York. So you'll see it's going to follow very similar to what we've been doing, except in this section here, we're going to be doing 2 samples. Thinking of what's ahead, we're going to do the same thing for means. I'll see you in class.